So large language models, LLMs, have become firmly established in the tech landscape. Now, many of us use them online with service providers like OpenAI with ChatGPT and so on. However, you can also run them locally on your PC, on a laptop, even on a single board computer. Now the question is what kind of size of LLM, how large does your large language model need to be to make it useful? In this video, I want to look at that question and to see whether you can actually get good, useful results out of something you are running on your local PC, which means you're not sending your data out onto the cloud for somebody else to look at. So if you want to find out more, please let me explain. Now the size of an LLM is expressed in the number of parameters it has. Now the parameters are the weights and the biases of the neural network. And so each one of those represents a neuron. The more parameters you have, the more neurons you have, the bigger the LLM. Now ChatGPT 3 had 175 billion parameters. Just try to visualize 175 billion parameters. And of course the newer models have way more than that. Now the models that you can run on your PC or on a Jetson or in Nano or even on a Raspberry Pi have much less parameters than that, maybe 1 billion, 3 billion, up to a maximum of 70 billion. So somewhere between 1 and 70 billion. But that's a big range. Are they good? Is it any good down at the 1 billion range? Or is it any good only? Do we get some decent results up at the 70 or somewhere in the middle? This is what we need to look at. Now to run an LLM, it needs to be loaded into memory, either conventional RAM or GPU memory. And large language models require more memory as their complexity increases. So the bigger the model, the more RAM you need. If you have 8 gigabytes of RAM, then you are limited to LLMs that are smaller than 8 gigabytes. So by the time you've got your OS running in your desktop and so on, 6, 7 gigabytes. Now every word, in the technical term for that is token, every token output by the LLM requires all of that memory to be accessed. So to get one token out, as I say, it's not really a word, it's half a word, let's say. All of that memory has to be processed. One go all the way through produces one token. Now each parameter, the weight and the biases we were talking about, at its best is a 32-bit number. So that's 4 bytes of memory. So to load a 175 billion parameter model, you're going to need around 700 gigabytes of RAM. You probably don't have that in your PC. I certainly don't. However, it turns out that neural networks don't necessarily need all the precision of a 32-bit number. So there are various methods where the weights and biases can be stored at a lower precision. What do I mean by lower precision? Let's talk about time. If it's 2 minutes to 2 o'clock and someone asks you the time, you may say it's 1:58 or 13:58. You may say it's 2 minutes to 2, or you might just say it's 2 or it's almost 2. So you're reducing the precision, and none of us really say it's 1:58 and 15 seconds. So we all use different levels of precision all the time in our lives, and you can do that in a neural network. You can store an approximation of the number. So if it's 1.51, well, you might just store 1.5 because it's close enough, something like that. Now, the generic term for reducing down the precision is called quantization. Now, storing parameters as 16-bit numbers rather than 32-bit numbers halves the amount of RAM that you need. But it's possible to go even lower, 8 bits or even 4 bits. Now, a 32-bit 2 billion parameter model takes 8 gigabytes of RAM. But a 4-bit version of the very same model can fit into 2 gigabytes of RAM. So that's obviously a huge saving there on the amount of RAM. So the question we're going to be looking at today is what happens when you take a 2 billion parameter model and shrink it down to 2 gigabytes rather than its full 8 gigabytes? Does it still work? Now, reducing the precision does reduce the quality of the model. Absolutely no doubt about that. When I said it was it's almost 2 o'clock, that's not actually the correct answer. The correct answer is 1:58 and 15 seconds, whatever. So data scientists quantify the model's loss of precision using a metric called perplexity. How confused the model is when making predictions. The lower perplexity indicates the model is better at predicting the next token in the sequence. However, it turns out the loss of precision and even a slight increase in perplexity still leaves the model functionally intact. In fact, there are some research papers that actually say that 4-bit models actually behave better than 8-bit models, or even better than 16-bit models, depending on the exact circumstances. So reducing this precision and even having a slight increase in perplexity doesn't necessarily mean the model falls apart. It's actually still very useful. Now, juggling with the number of parameters, so 2 billion models, 8 billion parameter models, and so on, and the level of quantization, do you want that in 32 bits or do you want that in 4 bits, means that we can have a 2 billion parameter model at 32 bits that fits into 8 to 10 gigabytes, as I said. Or similarly, we could have a 7 or 8 billion parameter model at 8 bits, which fits into 8 to 10 gigabytes. So you can have a model that is 4 times more complex, but you've reduced the precision, and yet it still fits in the same amount of memory. Now, this is what we're going to be looking at. What does that mean? And using quantization, you can even take a 70 billion parameter model at 4 bits, and you can make it fit into under 48 gigabytes of RAM. Now, not all of you have got 48 gigabytes of RAM, I'm sure about that, but it is not unheard of to have a PC with 64 gigabytes of RAM, for example. My laptop, as I'll talk about later, has 64 gigabytes. So then this poses these questions, as I've indicated. How useful are these models? How useful are they at the different sizes? 1 billion parameters, 2 billion parameters, 70 billion parameters. And does the quantization, 32-bit, 16-bit, 8-bit, so on, make any difference? Does it alter the usefulness of the model? Now, in this test, I'm going to be using various open source models that have been published by the big tech companies. You've got the Llama models by Meta, that's Facebook. You've got Gemma by Google. You've got Phi 4 is the latest, from Microsoft. You've got Granite by IBM. You've got Exa1 from LG. And even Alibaba have got one called Qwen. In this video, I'll be using the Qwen Coder, which is one specifically tailored to coding exercises. So here is a list of all the models. Now, you can pause the video there if you want to look into it, but it's worth looking here. There is a 1.5 billion parameter coder model. Notice this is the coder model from Alibaba that, when it's in 4 bits, fits into a gig of memory. So that's pretty impressive. And right at the other end of the scale here, we've got Llama 3.3, which is a 70 billion parameter model. And when you run that in 4 bits, you need 42.5 gigs of memory. Now, here's the interesting thing. If you look at Gemma 2, the 2 billion version of it, at the full 32 bits, takes 10 gigabytes of memory. But I could instead use Gemma 2, the 9 billion parameter model at 4 bits, and that fits into under 6 gigs. So I actually get a much bigger model in terms of its parameters in less memory by using the different quantization. The question is, does this make this one useful, or is this one more useful than that one? That's the kind of question we're going to be looking at. And the same we can see here for Exa1 from LG. The 7.8 billion parameter model at 4 bits is smaller than the 2.4 billion parameter model at its full 16-bit version. So that's some of the stuff we'll be looking at. Now, one thing to note is, because the size of the model means it's all loaded into memory and you need to process all that amount of memory every time you get a token, the smaller models produce more tokens per second. So Gemma 2, 2 billion parameters at 4 bits, you can get 44 tokens a second, which is pretty reasonable speed actually, and the results come up pretty quickly. And then this drops down when you then go to the 8-bit version. Well, then you drop down to half of that, literally 19 tokens a second. And if you go to the 32-bit version, then it drops down by a quarter now to 4 tokens a second. And then if you go to an even bigger model, let's say Phi 4 is a 14 billion parameters. When you're running that at 8 bits, it takes up 16 gigs of memory. You're getting down to 3 tokens a second. And when I load up the really big one, Llama 3.3, 70 billion, 4 bits, 42 gigs of memory, I'm getting half a token a second. So I had to wait a really long time for the answers. So processing speed slows down as the amount of data increases, and that's true of LLMs as it is true of so much of computer science. Okay, so we're going to start with a 1 billion model parameter because I wanted to see how useful are they. Now, of course, you can ask it a question like, what is the capital of France or something like that, or you could ask it about where is Big Ben, in the Houses of Parliament in the UK. It'll know the answer answer. It knows the answers to small, simple questions. But something that's more difficult, look at the following customer reviews and tell me which review was the most negative. And then there are 5 reviews here. It suits me well as described. It's brilliant. But number 4 is clearly worst keyboard I've ever used because it's too noisy. So these are actually real reviews that I've taken from a website of just some keyboard I clicked on. So, you know, the question we're asking is which one is the worst model. Now, let's actually try and run that now on a 1 billion parameter model and see whether it can do it. Okay, so here I am inside of LM Studio. I have Llama 3.2 1 billion instructions running at 8-bit loaded up. So we're going to hit send, ask it this question. The most negative review was number 3. I love this keyboard. Well, there you go. So no, a 1 billion parameter model can't do it. Now the good news is that 2 to 3 billion parameter models do get the answer right. This is Llama 3.2 3 billion instructions. Let's see how that does. The most negative review was 4. So there you go. So if you're looking for anything beyond, you know, what's the capital city of, and then you pick a country, if you're using, so I checked here, Gemma 2 billion parameters, Exa 1 2.4 billion parameters, Llama 3.2 3 billion parameters, and all of these at 4 bits, they were all able to pick review number 4 as the worst one and even describe what the problem was. The keyboard was too noisy. So you can start to do some useful sentiment processing, for example, using only a 2 or 3 billion parameter model, and those can be easily ran on any kind of desktop, on a laptop, on a Jetson Nano Orin, for example, Orin Nano. They'll all run on those very easily, and it'll actually give you useful output. Now I have a series of questions to test the capabilities of these LLMs at their different parameter sizes and their different quantization levels, and these are all things you can run on your home PC. Now I'm using LM Studio. I've got videos about LM Studio here on this channel. Llama would also be a good option and works equally as well. As I mentioned earlier, I have 64 gigs of RAM in my laptop, so that's an advantage for loading up some of these bigger models. It is a laptop with the RTX 2050 GPU with a small amount of shared RAM, 2 gigabytes I think. I do have a review of my laptop here on this channel. It's the MSI GF63 laptop, so if you want to see my views on this laptop, I have no regrets buying it. It still does exactly what I want it to do. Do check out that review. And I tried different size of LLMs at different quantization levels to see whether is the 8-bit one better than the 4-bit one, is the 32-bit one better than the 4-bit one. You know, I actually try it out. Okay, so question number 1, list all the marriage dates and wives of Henry VIII. So kind of a history question. Give me some facts. Ask the LLM to reproduce some facts. Now the small LLMs all got it right, regardless of the quantization level, because they gave minimum details. They literally just listed, you know, the wives of Henry VIII and maybe the marriage date, very little other details. Now the middle-sized LLMs, for example, Gemma 2 at 9 billion parameters, started to hallucinate. Their problem was they tried to be too clever. They give out too much input. They started to list who their children were that were born, or if they had children, or what the cause of death was, or, you know, all this kind of stuff. And when it started to do that, it did start to hallucinate, and some of the dates are wrong. Some of the children are necessarily, you might list a child and then add a second child on that wasn't as a result of that union, and so on. So they had a bit of a problem. But 5.4 at 14 billion and Llama 3.3 at 70 billion, 4 bits, both of these gave perfect verbose answers with all those extra details about why and who and where and all that, and it was all correct. So you can see that the smaller LLMs worked well when they didn't have to give out much output because they didn't give themselves much chance to hallucinate. The middle-sized ones started to hallucinate a little bit. Now maybe you could change the prompt to make sure it reduces the amount of output, and that would be an advantage. Now just to clarify, when I said all the smaller LLMs, I meant the 2 billion and above. The 1 billion one still doesn't do a good job. So what the takeaway is, the 4-bit versions of Gemini 2 billion perform just as well as the 8-bit and 32-bit versions. This is our first clue that the 4-bit versions work just as well. Quen Coder refused to answer because, of course, it's a coder LLM. So it says, I'm not programmed to tell you about history. I'm here to tell you about coding. And that's literally what it said. And the 3-bit version of Phi 4, which is quite surprising, performed just as well as the 8-bit version. And that's also true of Llama 3.3. The 3-bit version performed just as well as the 4-bit version. But very surprising here to see the 3-bit version performing just as well as the 8-bit version of Phi 4. Next question, correct the following spelling. All the words there in red have got some kind of mistake in it, kilometers with a C rather than a K, and so on. Now, all the LLMs did a great job, but the smaller ones generally fail to correct does span. So if we go back here, you can see the river does span an impressive, so the river spans would be the correct way to do it. So the smaller LLMs often fail that one thing, but the rest of the stuff they got right. Gemma 2 at 4 bits and XE1 at 4 bits corrected does span, whereas the 8-bit and 32-bit versions of those exact same LLMs didn't. Now, this could be due to the fact that, of course, every LLM has a random factor. They don't always give the same answer each time. There's a randomness factor to make sure it gives out, more interesting kind of responses. But it's interesting to note here that the 8-bit and 32-bit versions actually performed worse. But that could have been just a kind of a one-off. XE1 also has a habit of rewriting the text as well as fixing the spelling, so it didn't agree with my thing about the river taking 2,200 kilometers, and it put its own number in there and then converted the miles as well, and did things like that. So you've got to be careful there. Sometimes these LLMs can get away with themselves and start saying more than they need to. The 3-bit version of Phi 4 performed just as well as the 8-bit version, as in that previous answer, and again the same with the 3-bit and 4-bit versions of Llama 3.3. So again, doesn't seem to be an issue with the quantization. Now here's a good one. How many vowels in total, including repeats, are in the word elimination? The correct answer is 6, because, for example, I appears in there 3 times, and you've got an E, an A, and an O as well. And what do we see? Well, none of the smaller LLMs got that right, because LLMs are bad at counting, and smaller LLMs show that. This was true, when ChatGPT first came out, ChatGPT 3 or whatever, it's terrible at counting, and so they couldn't do it. In fact, only Phi 4 and Llama 3.3 gave the right answers, and that's Phi 4 even at 3-bit. The quantization level didn't alter the results. So that's really interesting. Also, the 32-bit versions of the smaller LLMs didn't do any better either. So the 32-bit version of Gemma 2 at 2 billion parameters didn't learn to count any better than the 8-bit or the 4-bit version did. Now here's another one. You are an English teacher helping a student with an exercise. It's important that you follow these instructions precisely. Read the following text, then pick the most unusual word. Find a one-word synonym for that word. Take that synonym and reverse it. And I again give an example. The reverse of spoon is noops. And then I give it the text here. Now there's some interesting words here in this text, but this one here, quixotical, okay, it comes from, Don Quixote, but it's spelt the same but pronounced differently. So this word here is the most unusual word in that text. All the LLMs were able to pick out quixotical as the most strange word, and they were all able to pick a synonym. So idealistic, fanciful, adventurous, ambitious, etc. They all came up with that. But all the LLMs failed to reverse the word that they picked, except for one, and we'll talk about that in a moment. Now, some of the reversals were terrible. For example, Exa1 said the reverse of idealistic, which was the synonym it chose, is dash silalid, including the dash output there. So it's just completely wrong. Others missed it. If you look at this, that looks almost right, but notice here it's IED rather than IDE. So it's just got it slightly wrong in the reversal of it there. Only Phi 4, 14 billion parameters managed to do it correctly, both the 3-bit and the 8-bit versions. Even Llama 3.3, 70 billion, didn't get it right. Take the phrase Gary explains, count the number of alphabetic characters in that phrase, ignore punctuation and spaces, multiply that by 7, convert the product to a hexadecimal number, reverse the digits of the resulting hexadecimal number. What's the final answer? Well, the answer is 4,5, because it's 12 times 7 is 84. 84 in hex is 0x54, and so that's 4,5. Now, again, the smaller LLMs all fell because of the counting mainly. They did the rest of the steps, but they said there's 20 characters in Gary Explain, there's 10 characters in Gary Explain. It just basically gets it wrong. Coda really interesting, did a really good job. It's only a 3 billion parameter model. It did a really good job, both the 4-bit and the FP16-bit versions of it. And again, back to the old stable here, 5.4 14-bit and Llama 3.3 both gave perfect answers. So these are always proving to give really good answers for many of these questions. The 3-bit version of 5.4 again performed just as well as the 8-bit version, and the same again with Llama 3.3, 3-bit versus 4-bit. Another question, write a program. So here's write a Python program. So rather than doing it themselves, write a Python program to do that thing. Take Garrett explains, count the number, reverse the, and so on. Now, the following LLMs completed the task perfectly. Quen 3.5 Coda, only a 3 billion parameter, did it perfectly. So that's a really strong performance there. And also from Exa1, a strong performance. The rest of the LLMs didn't manage. They all produced Python code, but it had an error in it. And they seem to have a particular weakness about reversing the number and using some fancy indexing stuff. I'm sure if I'd then said to it, well, there's a bug on line 7, please fix it, then and gave them another go, they may have fixed it. I didn't try that. I wanted just the one shot. So again, Llama 3.3 and 5.4 did it excellently. So strong performances there from the Coda LLM, which is really what you'd expect, but it means it's very useful at only 3 billion parameters. And Exa1 also did a very good job as well. Again, quantization level made no difference. It worked or it didn't work regardless of the quantization level. Alice has 5 brothers and she has 3 sisters. How many sisters does Alex's brother have? Well, the answer is 4, because there are 3 sisters besides Alice, and then Alice herself. Now, only Llama 3.3 70 billion, both 3-bit and 4-bit, gave the correct answer. But to be fair, even the big ones that we can find online, like Gemini 1.5 Flash 8 billion and GPT 4.0, they gave the wrong answer. You have to go up to O1 Mini or to Gemini 2.0 Flash to get the right answer out of the online ones, the bigger ones. Okay, final question. This one really is hard for these LLMs. You have 2 hourglasses, one that measures exactly 10 minutes, another one that measures exactly 5 minutes. Using only these 2 hourglasses, can you measure exactly 15 minutes? If so, explain the steps involved. Now, the simplest answer is you turn over the 10-minute one. When it's finished, you turn over the 5-minute one, and that's 15 minutes. Now, that's actually really hard for an LLM to answer. None of the LLMs, local LLMs that I'm running, managed to answer that consistently. Some got close. Some had the right answer buried in a whole bunch of fluff. For example, some of them were getting you to turn the 10-minute one over even when you weren't using it, and then turn the 5-minute one over, and then turn the 10-minute one over again, and then turn the 5-minute one over again. And it was doing it. And if you did do it, you would get 15 minutes. But there was lots of fluff, or it was convoluted, or it was inefficient. But to be fair, GPT 4.0 and Grok don't give you the right answer for that either. Again, you need to go up to O1 Mini. Claude 3.5, Sonnet and Gemini 2 Flash Thinking gave the right answer. But we are talking much bigger models running up in the cloud, and some of those didn't give you the right answer. So to be fair, that was to be expected. So what are the conclusions? Well, the first conclusion is that you should use the biggest model that you can. Depending on how much RAM you've got or GPU RAM that you've got, use the biggest model that you can. And you should always use the Q4, the 4-bit quantization. It's going to give you that best match between size in the RAM, but also the functionality. In fact, if you have a choice between a smaller, less parameters large language model, let's say 2 billion, but at 32 bits or even 16 bits, compared to, let's say, a 9 billion parameter one but running at 4 bits, go with the 9 billion parameter. It's certainly the size that matters here. 9 billion parameters, even at 4 bits, is going to perform much better than a full precision 2 billion parameter model. You should also check out specialist LLMs like the Coda one if you're aiming just to do kind of coding tasks. Now, overall, I think looking at all these different models or all these different sizes, for me, the 5.4 one from Microsoft came out on top. 14 billion, which means it is quite big and it is going to take up some memory, but it's not going to grind your machine to the ground. It's going to run and it's going to give you some decent results. So I think well done to Microsoft for 5.4. Okay, that's it. My name's Gary Sims. This is Gary Explains. I really hope you enjoyed this look at large language models, the number of parameters, the quantization, how well they perform on your PC. If you did, please do give this video a thumbs up. And if you like these kind of videos, why not stick around by subscribing to the channel? Okay, that's it. I'll see you in the next one.